This presentation is on statistical process control, or SPC. And I include this topic in this class because it is an important part of manufacturing. And every single manufacturer I've ever dealt with has used some form of statistical process control. And it can be used for anything in reality. It can be used to monitor, streamline home loan processes. It could be used to monitor filling bottles of spices. It could be used to monitor filling bags of salads. It can be used to monitor the efficiency of putting car tires on at a tire facility. Anything can be monitored with SPC. The issue is, when is it worth it? And you can't measure everything. You have to make a decision which things are critical to monitor, either because of customer demands, regulatory requirements, or a desire to focus on a particular measurement for some efficiency, profitability within the company. So you can see here, this was done for McCormick and Company. And this was a project I was involved on years ago. I never worked for them, but I did provide some consulting when I was working for another company. And so this was for training of manufacturing individuals at the Salinas McCormick plant in their quality assurance department. So where is SPC currently in use and who uses SPC? Well, the SPC is currently in use in, like I said, damn near every manufacturing facility imaginable. There is something that they are monitoring. And you have to decide, what is the one or two or three things that you can monitor that is going to make the most difference in your company, in your situation. Excuse me here, getting too much road noise. Anyway, what are the one, two, or three things that you can monitor that are going to help you understand if your process is stable and efficient? Who uses it? Every food manufacturer and other manufacturers around. Everybody in manufacturing uses SPC. So keep in mind that this is a training PowerPoint for actual quality control employees at a McCormick facility. McCormick's goal is to continuously produce materials within legal limits of label weight requirements while minimizing overfills. Makes sense? And so they're looking at weight requirements. They're filling bottles with spices. What is one of the most important things to monitor that makes sense with SPC? You're selling spices by weight. Monitor weight. You could measure length of baby carrots. You could measure a lot of different things, but weight is one of the more common ones in food because that's how you're being measured by the government in terms of legally meeting your label requirements. If I sell a 1 pound bag of salad, can I sell you a bag of salad that's less than 1 pound? Yes, if it's within a very small range of less than 1 pound, but an entire pallet of bags or a whole case of bags, depending on how it's being measured, cannot be less than 1 pound each on average. Individual bags can be under by a tiny bit. And I'm not going to get into the details of exactly how much you have, how much under is okay. You can never be under by lot or by load or by palette or grouping, however you're identifying that. The primary objective of SPC is to detect out of control situations and their assignable causes before producing non-conforming units such as underweights. So out of control, we'll talk about out of control, but it means that you're making a product that's not stable for some reason. You're putting too much or too little or kind of an inconsistent amount. It's just bouncing around too much. And if the weight is unstable, you consider that out of control. Or if it's shifting gradually, they're getting heavier and heavier and heavier, that's out of control. So you want to make sure that you never give your customers a product that's underweight. And I don't mean, like I said, I don't mean an individual bottle that's just a little under. I mean a pallet of bottles where the average is under. You cannot do that. It is illegal. And underweights in food is generally the most important SPC tool. So assignable causes. Why are we having problems? Variation in raw materials. So imagine this. One variety of oregano is very open and flat, thin, light, fluffy leaves. And you grind it up and now you've got this oregano that doesn't fall down together. It's very fluffy and light. I've got another version that is like little rocks. The leaves are thicker, heavier, denser. You grind it up and the same amount of product can be, in terms of weight, can be much less in terms of volume. And you're selling these by weight. So that's an issue. You might have some product that's stickier. So I've got some leaves that have little hairs on them and they stick together. And so that creates problems in the scales. Things get sticky and sticking to the sides. Now the scales aren't weighing properly or they're not filling smoothly into the bottles because of variation on the raw material. And I'm just talking about oregano. Imagine all the different variations you can have with carrots and cabbage and lettuce and spinach and on and on and on. There are all kinds of problems where you're running an operation with materials that is not always the same. It's not like making an automobile where the differences from one steering wheel to the next are trivial. They're almost identical. They should be almost identical. They're machined pieces and everything should be the same. They're machined or molded or something that makes all of the pieces identical. So the idea that things will be different from, one Ford Mustang to the next as you're putting them together, you shouldn't see those kinds of problems. They have their own issues. It's not like making cars is easy, but making food products certainly has a whole bunch of variation introduced because of the raw materials, the biology of the different varieties. What about improper machine settings? Or maybe even a machine that has screws coming loose or something like that. There are all kinds of reasons why your packaging isn't going the way you think. And operator errors. Operators don't load things correctly. They're not setting the machine at the right speeds, et cetera, et cetera. There are lots of things that can go wrong. So we'll look at SPC, what it is. We won't do the histogram exercise. I left that in just because it was something done in the live training. We'll look at weight control charts. There won't be an exercise, but I'll show you some examples of manually produced weight control charts. They've all moved to a digital form now. And we won't get into the evaluations either. So after this training, you will understand more about histograms, normal distribution and its characteristics, control limits, sampling, weight control charts or weight sheets as they were called in the industry at McCormick, action points, maximum allowable variation, and the SPC, Statistical Process Control tools. Okay, so those are some of the vocabulary words of things you should get from this presentation. So first of all, histograms. Histograms are frequency distributions used to plot observations from a sample population made up of measurable data. And it can be weight, it can be length, it can be anything you can measure. So let's look at this. It's hard to read, but this is length in millimeters on the bottom or x-axis and number of times observed on the y or vertical axis. So how do you create this chart? Just imagine you have little squares. So you see right here under 45 millimeters or above the 45 millimeter on this chart, I have one box. You can see it's one. I also have one here at 65 as well, all right? So for every time I observe a particular length of whatever I'm measuring, think of this as measuring baby carrots, I put a box there. So I've got 3 boxes because I observed doing this sampling. I observed 46 3 times. I observed 47 5 times. I observed 48 6 times. So there's 6 boxes there, even though you don't see the individual boxes. But you just keep putting a box on top of the measurement. And when you're done, you end up with this pattern, which we'll soon learn about. It is relatively balanced, not perfectly, but it's relatively balanced with a strong average or mean in the middle and tailing off to the extreme low and the extreme high. By the looks of this, my cutter was aiming for 50 millimeters. Sometimes it did it a little short, sometimes it did it a little long. On rare cases, I got 45 or 55, but most of the time I was between 46 and 54, I think that is. Or 54, 55, whatever. I can't read those numbers too well. It doesn't matter. Bottom line is I have what's called a normal distribution. So we're not going to do an actual exercise with baby carrots. We're not going to grab baby carrots and measure them, but just imagine that's what we did to create that previous chart. And so here you can see how a line has been added to approximate the curve of this distribution. And we call that a normal distribution when it's approximately symmetrical, or it's a symmetric histogram, which means it has a peak in the middle at the average or mean, and it tails off relatively similarly on the low side and the high side. And you can see this isn't perfect, but it certainly is a normal distribution, something that you would expect to see very frequently. And there are all kinds of things in manufacturing that follow normal distributions. There are other types of distributions out there. There can be distributions where the peak is at one side and it has a long tail on the other side, and things that even have 2 humps instead of one. The 2-hump camel histogram or distribution has its own special situation. Certain bird populations, if you measure their beaks, you might get a double histogram, because a short beak is really good for breaking seeds. A long beak is really good for picking out insects, but in between, it's not as good. So there aren't as many birds in between because it's a disadvantage. You're not really good dealing with seeds, and you're not really good dealing with insects. So you end up in some bird populations having this little double hump when you're looking at beak sizes. But here's one example of a skewed distribution. Now, if it was skewed in the opposite direction, human birth weight of natural childbirth. There's a point at which, I mean, it's not this dramatically skewed, but there's a point at which it's just too big of a baby, got to do C-section. So natural childbirth, there's an upper limit due to physical constraints. And so you can have small babies, you can have big babies, but it's rare to have really, really, really big babies as a natural childbirth. So that's a type of naturally occurring skewed distribution. So what are the main characteristics of a normal distribution? If I took everybody at Hartnell College and took their height or weight, I could plot that, and I'd probably end up with pretty close to a normal distribution. There would be an average, or mean is the proper statistical term. And then there's variation. How far out from the mean does the data spread? So if I'm making something like ice cream scoops, I work at an ice cream place like Baskin Robbins or something, and I'm making ice cream scoops, and somebody's testing me and doing random sampling of the ice cream scoops I make. How many grams is each scoop? There might be quite a fair amount of variation. I'm not perfect. I do a good job, but there's variation. Is that okay? Sure it is. You can't expect to be perfect in that regard. But if I'm making ball bearings for automobile tires, each bearing has to be very precise. Is there still variation? Sure. Nothing is absolutely perfect. And so if I'm measuring the size and roundness of the ball bearings, there's going to be some variation, but the variation is going to be very, very tiny. Ice cream, I got a lot of slop. I don't have to be that accurate. Ball bearings, I've got to be very accurate, right? So variation is the spread of the data. Now, if I'm making ball bearings for automobiles, that's one level of accuracy. If I'm making ball bearings for NASA on their space program, I have to be tighter still, right? If I'm making ball bearings for a $2 toy car, some piece of junk throwaway toy, I can have more spread in the data. The bearings have to work, but they don't have to be good, right? So again, variation. So another couple of examples. Here's driving time. Driving time from point A to point B, 19 minutes, 20 minutes, up to 24 minutes. Usually it takes you 22 minutes, but depending on traffic and traffic lights and things, it can take you less or more. Clock in times. So this is a work shift that starts at 6 o'clock. And you can see here that at 5:55, you get people clocking in. 5:57, or 8, they're clocking in like crazy. And by 6:01, the last person is clocking in. The last 3 people are clocking in a minute after the shift. Don't be those 3 people clocking in after the shift. Characteristics of the normal distribution: the mean, or average, is the average of the values for the sample population. So you add it all up and divide by the number in the sample. So if I do, well, means, I don't have to worry about it. In our application, the mean of all samples from a run must be at or slightly above the label weight. So how you define a run, companies can have a little bit of leeway in the definition, but the government only allows a little bit of leeway. So your mean has to be at or above label weight. Otherwise, you're cheating your customers, you get fined. And so that's part of the regulatory process to control manufacturers, to say that if you're selling 1-pound bags, you better be given 1-pound bags, at least on average. No individual bag can be under by very much, but an individual bag can be under by a little bit, as long as across the run you're giving at or above the label weight. So what's the solution? Crank it up above the label weight and you don't have to worry about it. Wrong. You don't want to crank it up above the label weight so you don't have to worry about it, because then you're throwing away money. You're throwing away product. You're giving more than you have to. Now, yeah, there are situations where you might be able to do that, and it might be appropriate, especially for a product where the price of what you're giving away is very minimal compared to the cost or the charge of revenue that you're receiving for that product. And so by always giving a little more, you've got a happy customer at a very, very low price. But for most food products, the margin of profit is very small. And so you can't be giving away product. You want to be hitting very close to that label weight. You say it's a 1-ounce bottle of oregano, you want it to be an ounce. Now, yeah, you don't want to push it too close. You don't want it to be exactly an ounce when you're filling those bottles, because you don't want to have a whole run that's slightly under. So you might just do it up by a tiny, tiny bit above the label weight. So the target on the weight control charts is always slightly above the label weight for that reason, but it's slightly. It avoids your legal liability of going below the label weight on that run. The risk is too high. You definitely don't want to go below. So you basically dial the machine. If it's a 1-ounce bottle, you dial the machine to be just the hair above that 1 ounce. The variation tells how the data spreads out from the average. So a very wide spread, there's a lot of variation in the data. So if I'm looking at heights of all students at Hartnell, you're going to have quite a few people that are pretty short and quite a few people that are pretty tall, but most of the people are somewhere here in the middle, 5'6", 5'8", 5'10", the occasional 6'5", the occasional 4'9". There's all kinds of variation, right? We're measuring bags of salad or something, we would have a tighter amount of variation, but it's not as precise. We got big old chunks of lettuce and carrot and cabbage. Trying to get them all exactly the same is pretty tough. So you get close. So let's take a break.